Welcome! Today we'll explore windowing and window functions in digital signal processing. We'll show why it is essential for clean spectrum analysis, how different windows behave, and when to use them. Stay tuned until the end, where we'll demonstrate these concepts in MATLAB. Let's begin with a simple signal, an infinite continuous sine wave at 4 Hz. Its spectrum contains just 2 sharp spikes, called Dirac deltas, at -4 and +4 Hz. But here's the problem. You can't record an infinite signal. In practice, we only capture a portion of it. To do this, we multiply the signal by a window function. This process is called windowing, and it gives us a finite signal, for example, lasting just from 0 to 1 second. Now let's look at what happens in the frequency domain. A rectangular window has a spectrum shaped like a sinc function, and as you may know, multiplication in the time domain becomes convolution in the frequency domain. So convolving the Dirac deltas with the sinc function shifts and smears them out. The spectrum of our finite signal still has peaks at ±4 Hz, but now it also shows unwanted ripples, known as side lobes. This effect is called spectral leakage, and it happens because of the abrupt on-off switching of the rectangular window. The problem with these side lobes is that they can hide or distort weaker components of the signal. That's why it's important to reduce them. One way to do this is by using alternative window functions, the triangular window for instance. Unlike the rectangular window, which has an abrupt on-off transition, these windows taper smoothly from the center to the edges. This smooth tapering dramatically reduces the spectral smearing and the amplitude of the side lobes. But there's a crucial trade-off. Using any window other than rectangular will also affect the signal in the time domain. The tapering reduces the amplitude of the samples at the edges, which effectively lowers the total energy of the analyzed signal. That's why many different window functions have been developed. Each represents a unique balance of properties. In an ideal case, a window would have a very narrow main lobe in frequency, strong side lobe suppression, and minimal distortion in time. But in practice, these 3 goals are in direct competition. Improving one usually means sacrificing another. Now let's look at some popular window functions. We'll start with the rectangular window, which we've already seen. It gives the sharpest main lobe, so frequency resolution is excellent, but the side lobes are very strong, making it the worst for leakage. To reduce that leakage, we use windows that taper smoothly. A very common choice is the Hamming window. It offers a nice balance. The main lobe is slightly wider than rectangular, but side lobes are much lower. Another widely used option is the Hann window. Compared to Hamming, its main lobe is a bit wider, but its side lobes drop off much faster, making it very popular for general-purpose applications. When you need to detect a tiny signal right next to a strong one, you need higher dynamic range. That's where the Blackman window comes in, with excellent side lobe suppression. Finally, for applications that demand precise control, there's the Chebyshev window. Its unique feature is that all side lobes are the same height. You can even set the side lobe level yourself, and the window will minimize main lobe width for that value. This makes it especially powerful when designing filters with strict leakage requirements. Now let's move to the final part of the video, putting our windowing knowledge into practice with MATLAB. The full simulation code is linked in the description below. We'll start with the parameters. First, we define the sampling frequency of our signal and set to 1000 Hz. Next, we choose a carrier frequency of 10 Hz. Finally, we set an oversampling factor of 10, which will give us finer frequency resolution, so we can clearly observe the effects of different windows. In the next section, we generate the window functions. For this demo, we'll use rectangular, Hamming, Blackman, and Chebyshev windows, and we'll also assign labels to keep track of them. For each function, we pass a sampling frequency as a parameter to control the total number of samples in the generated window. Finally, we plot each window function. As you can see, the shapes in MATLAB match exactly with the theoretical windows we discussed earlier. Next, let's generate our test signal. We'll start by creating a time vector with samples spanning 1 second. Using this, we generate a 10 Hz sinusoid. Now it's time to apply windowing. Since we want to test 4 different windows, we duplicate the sinusoid into a matrix with 4 identical columns. Then, we perform element-wise multiplication so that each column is multiplied by a different window. Finally, we plot the results. Notice that with the rectangular window, the signal remains unchanged in the time domain. But with the other windows, the sinusoid is smoothly tapered at the edges, following the shape of each window. In the final step, we calculate the spectrum of each windowed signal. First, we define the frequency vector, keeping only the positive frequencies. Then, we apply the FFT along the first dimension of our signal matrix, using the oversampling factor to improve resolution. Next, we discard the negative frequencies and plot the results. As you can see, the spectrum of the sine wave with the rectangular window has the sharpest main lobe but very poor side lobe suppression. Moving through the other windows, we trade main lobe sharpness for better side lobe attenuation. Finally, with a Chebyshev window, the main lobe is much wider, but the side lobes are strongly suppressed. This clearly shows the trade-off, narrow main lobe versus side lobe attenuation, and each window offers a different balance. And that wraps up today's video. If this video helped you, be sure to watch more from our DSP Fundamentals playlist. Thanks for watching, and see you next time.